Now let's continue our discussion of properties of the liquid state. In the previous lecture, we had talked about three different properties of the liquid state: viscosity, surface tension, and molar heat of vaporization. Now I want to talk about the fourth property, vapor pressure. So let's develop a definition for vapor pressure. It's kind of unwieldy to define, but just bear with me. I want you to think about a liquid in a sealed container. So let's draw a sealed container with a liquid in it. So in our sealed container, okay, so imagine we have a cap on this. This is a sealed container. We have a liquid phase, the condensed phase, and above it we have some head space where we have gas molecules. Now, we have constant phase transitions between the gas and the liquid phases. So liquid molecules will be volatilizing into the vapor phase, and vapor molecules will be condensing into the liquid phase. Okay, and this is going on constantly. Okay, you have molecules transferring back and forth. So if you have a sealed container, there is an equilibrium point reached at which the number of molecules leaving the liquid to make vapor is equal to the number of molecules leaving the vapor to form liquid. Okay, that's an equilibrium between these two phases here. So you have to imagine that even though there is constant change between the liquid and vapor phases, there's a point at which the number of molecules going in each direction equalizes. So at this equilibrium point, the number of vapor molecules, as well as the number of liquid molecules, is finally constant. So all of that goes into the definition of vapor pressure, because the pressure under these conditions in that sealed container is what's defined as the vapor pressure. So you can think about the vapor pressure as the pressure exerted by the molecules in a head space over a liquid. Okay, equilibrium vapor pressure. Now, think about what happens to vapor pressure with temperature. Okay, vapor pressure, I'm going to abbreviate as PVAP. PVAP is the abbreviation for vapor pressure. As temperature goes up, what do you think happens to the pressure exerted by the gas molecules in this headspace here? Oops, in that headspace here. I erased it by mistake. What happens? Well, think about it. As temperature goes up, more of the liquid molecules are going to volatilize into the vapor phase. So you're going to have more pressure exerted in that headspace. So vapor pressure is always going to increase as temperature increases. So the higher the temperature, the higher the vapor pressure. Now, let's think about various liquids. Compounds with low vapor pressure would have what? Comparatively weak or comparatively strong intermolecular forces. Let's think about that for a second. If you have low vapor pressure, that means that your molecules are more likely to stay in the liquid state because of their strong intermolecular forces. So low vapor pressure corresponds to stronger intermolecular forces. Conversely, the higher the vapor pressure, the weaker the intermolecular forces. And this is because strong intermolecular forces encourage molecules to remain in the liquid state because they're more attracted to each other. So let's put this concept into practice to answer a couple of questions. Which of the following compounds has the highest vapor pressure? Carbon dioxide, water, or sulfur dioxide? So to answer this question, we need to consider the polarity of each of these compounds. And in order to figure out the polarity, you have to draw the Lewis structure, okay? So polarity is the key to answering questions like this. So you need to be able to draw Lewis structures. So carbon dioxide, if I draw its Lewis structure, it's a linear molecule. And though it contains polar bonds, The bond dipoles go in equal and opposite directions, so the dipoles cancel. And carbon dioxide is actually a nonpolar molecule. Therefore, the strongest forces present are going to be London dispersion forces only. All right. Well, water we know is very polar, of course, because of its bent structure. So that bent structure means we have a high degree of polarity, and what's more, we have oxygen and hydrogen directly bonded to each other. So water has hydrogen bonds. Now, we know that hydrogen bonds are very strong intermolecular forces compared with London dispersion forces. Finally, sulfur dioxide. We have to draw the Lewis structure. Okay, so you can review that if you need to, how to draw Lewis structures, because this is crucial to telling whether a compound is going to be bent or not. Now, sulfur dioxide, that sulfur has 6 electrons associated with it. Sulfur dioxide is going to have bond dipoles. And because of its bent structure, it is definitely polar. Okay, so CO2 and SO2 are very different molecules because of the extra electrons on the sulfur. However, we don't have any hydrogens in this molecule, so the strongest intermolecular forces at play are going to be dipole-dipole forces. So 3 different types of forces. The hydrogen bonds are going to be the strongest forces. Strongest forces are going to mean lower vapor pressure. Okay, hydrogen bonds, so that's going to be the lowest vapor pressure. Conversely, the compound with the weakest intermolecular forces, in this case, the London dispersion forces, the weakest intermolecular forces is going to correspond to the highest vapor pressure. So the answer in this case would be carbon dioxide. Because it is nonpolar and it has the weakest intermolecular forces, it is going to have the highest vapor pressure. Water, with its strong hydrogen bonds, would have the lowest vapor pressure. All right, so now let's move on to a related concept, the 5th property of the liquid state that we're going to talk about, which is boiling point. Now, different liquids have different boiling points, and you probably have conceived of the boiling point as the temperature at which a liquid boils, at which a liquid goes to vapor. And that's a pretty good way to think about it. It's actually an equilibrium concept where you have a temperature where you have molecules going in both directions. So the technical definition of boiling point is the temperature at which the liquid vapor pressure is equal to the external pressure. Now, a lot of times we will refer to normal boiling point. That adjective, normal, refers to the boiling point temperature at which the liquid vapor pressure or the external pressure, however you want to think about it, is equal to 1 atmosphere. So this would be sea level, right? External pressure is equal to 1 atmosphere. So usually when you're looking up boiling points of a liquid, you're referring to the normal boiling point. So the normal boiling point of water, for instance, is 100 degrees Celsius or 212 degrees Fahrenheit. This is because boiling point is very dependent on external pressure. Okay, so if you're at sea level, like in New York, you have basically normal boiling points. But if you go up, for instance, to very high altitude in the mountains, you are reducing the atmospheric pressure. And by reducing the external pressure, you're reducing the boiling point as well. That's why recipes are different at high altitude. Okay, foods just cook faster at higher elevation because the external pressure is lower, the air pressure is lower, and that means that you're reducing the boiling point. So in the lab, for instance, if we put a vacuum on a sealed system, we can reduce the boiling point because we're reducing the pressure under vacuum. Okay, so let's think about what this means in terms of intermolecular forces. The higher the boiling point, the what the intermolecular forces. Well, let's think about that. A higher boiling point means that you need more heat to disrupt the intermolecular forces and make the liquid go into vapor. So the higher the boiling point, the stronger the intermolecular force is. Strong intermolecular forces means that you're going to need higher temperatures to vaporize your liquid. Okay, so I hope that makes sense. We can use that information to answer a couple of example questions. 2 examples. Let's do this one first. Which of these 2 compounds has a higher boiling point? Hydrogen molecule or the fluorine molecule? So H2 or F2? All right, well, look at these molecules. They're both nonpolar, right? If we draw these molecules, they're very simple homonuclear diatomic molecules. Only difference is that if I draw their Lewis structures, fluorine has a whole lot of electrons around it. So these are both nonpolar molecules. So that means they're both going to have London dispersion forces, LDF, as the strongest intermolecular forces. So to break the tie, we have to look at which one is bigger. Well, fluorine is bigger. It has more electrons. The fluorine atoms are bigger than the hydrogen atoms. So this is an instance where the polarizability of F2 is greater than that of H2. Okay, we simply have more electrons and more opportunity for instantaneous dipoles. So F2 is going to have stronger London dispersion forces than H2. So what that means, well, which one is going to have the higher boiling point? Higher boiling point comes from stronger intermolecular forces. So we would expect the higher boiling point to belong to F2. Okay, so I hope that makes sense. I'm going to give you the data. All right, so here are the normal boiling points. If you look them up for these 2 molecules, you can find hang on a second. Let me try to write that in a coherent way. The normal boiling points for these 2 molecules. So these are the boiling points at 1 atmosphere of pressure. So for hydrogen, it's about minus 253 degrees Celsius. Very negative. Okay, this is one of the lowest boiling things out there, right? So, and then for fluorine, it's also negative. Again, this is a very low boiling compound. This is about negative 188 degrees Celsius. So they're both nonpolar, they're both small molecules, they're both very low boiling, but hydrogen is lower boiling than fluorine by quite a lot, okay? By what, 50, 60, almost 70 degrees Celsius. So this makes sense. The higher boiling point, in this case, the less negative boiling point, belongs to fluorine. Higher boiling point arises from stronger intermolecular forces. Let's do one final example. Which has a higher boiling point, carbon dioxide or sulfur dioxide? So as we said a moment ago, carbon dioxide is nonpolar because of its linear structure. Sulfur dioxide, by contrast, is polar. The strongest intermolecular forces at play in carbon dioxide are London dispersion forces, and the strongest intermolecular forces at play in sulfur dioxide are dipole-dipole forces. So dipole-dipole forces are much, much stronger than London dispersion forces. So we would expect a higher boiling point for sulfur dioxide. Let's look at the data. Here are the normal boiling points for carbon dioxide and sulfur dioxide. Carbon dioxide has a normal boiling point of minus 78 degrees Celsius. Sulfur dioxide has a normal boiling point of minus 10 degrees Celsius. So again, we're still in the negatives here for these relatively small molecules. But as you can see, carbon dioxide's boiling point is much lower than sulfur dioxide's boiling point. So the prediction bears truth. That polar molecule, sulfur dioxide, has a higher boiling point because of the strength of its intermolecular forces. So looking at the polarity of different compounds will help you predict their relative differences in their boiling points.